Ever wonder how you could tell what someone is growing like halfway across the world just by looking at a picture from space?
It's pretty wild.
Yeah.
Yeah.
Today's deep dive is all about that. We're going to explore how satellite imagery is being used to identify different crops.
Mhm.
You might be surprised to learn that researchers in Croatia are using images from the Sentinel-2 satellites
Oh, wow.
and machine learning to do just that.
What's fascinating is that this technology, it isn't just for scientists anymore.
Right.
It's becoming increasingly accessible to farmers, environmentalists, and anyone who's interested in understanding the Earth's surface.
That's what I love about this topic. It feels like something straight out of science fiction,
Uh-huh.
but it has very real and practical applications today.
Yeah,
But before we get into the nitty-gritty of crop identification,
sure.
we need to understand the eyes in the sky that make it all possible. The Sentinel-2 satellites.
Right. These satellites are constantly orbiting the Earth, capturing sunlight that's reflected back from the surface.
Okay.
They're like our planet's personal photographers, constantly snapping pictures in 13 different bands of light.
Wow.
Each band represents a specific region of the electromagnetic spectrum, from visible colors like blue and green to invisible infrared wavelengths.
Okay, so instead of seeing a pretty rainbow, we get 13 different sets of data about what's reflecting light down on Earth.
Exactly.
It's like having 13 different pairs of glasses, each giving you a slightly different perspective on the same scene.
Exactly. And here's where it gets really interesting.
Okay.
Each object on Earth, a tree, a building, a field of wheat, reflects different amounts of light in each of these bands.
Uh-huh.
By analyzing these subtle differences, we can start to identify what those objects are.
So imagine being able to see the health of a plant just from the subtle way it reflects red light.
Right.
That's the kind of information these bands can provide.
It is. It is remarkable. Let's start with the first band, B01.
Okay.
This band captures light in the deepest blues and violets, wavelengths that are particularly good at detecting particles in the atmosphere, like smoke or dust.
So not exactly X-ray vision for crops, but understanding the atmosphere is important too, right?
Absolutely. Atmospheric conditions can affect the clarity of the other bands.
Okay.
So having information from B01 helps us refine the overall picture.
Gotcha.
Now, moving along the spectrum, we come to B02,
Okay.
which captures blue light. This band is crucial for distinguishing soil from vegetation and even helps in mapping different types of forests.
Okay, so B02 helps us see the big picture, where the forests are, where the fields are.
Right.
What about B03?
B03, capturing green light, allows us to peer into the depths of clear water.
Oh, cool.
It's like having a superpower to see beneath the surface of lakes and rivers, identifying areas of pollution or algal blooms.
Ah, so we can see the health of water bodies too. This is already more than just X-ray vision for farms.
Yeah.
But let's get back to the crops.
Okay.
What's next?
Next up is B04, capturing red light. This is where we start to get into the really interesting stuff for understanding plant life.
Okay.
You see, healthy plants absorb a lot of red light for photosynthesis,
Right.
while unhealthy or stressed plants reflect more of it.
Hold on. You're telling me we can actually tell if a plant is struggling just by how much red light it reflects?
Precisely. And it highlights just how much information is hidden within these seemingly simple bands of light.
Yeah.
But we're just getting started. Now buckle up, because we're about to enter what's called the vegetation red edge.
The red edge sounds dramatic.
Yeah.
I'm all ears.
It is pretty cool.
Okay.
This region of the spectrum, covered by bands B05, B06, and B07,
Okay.
is all about the subtle ways healthy plants reflect near-infrared light. It's like plants have a secret language, and these bands are giving us the key to understanding it.
So the more light a plant reflects in these red edge bands, the healthier it is.
You got it. And by analyzing the subtle differences in reflection across these three bands,
Okay.
we can go even deeper, learning about a plant's chlorophyll content, its stage of growth, and even how much water it's getting.
Wow, it's like we're getting a full medical checkup on these plants from hundreds of miles above Earth.
Right.
What comes after the red edge?
Next up is B08,
Okay.
the star of the show when it comes to analyzing vegetation. This band captures near-infrared light,
Okay.
which plants reflect strongly, and it's incredibly helpful for understanding things like biomass, vegetation density, and even shoreline mapping.
NIR. That
Yeah.
sounds familiar. Isn't that what they use in those night vision goggles you see in spy movies?
You're not wrong. Near-infrared light is all around us,
Okay.
and it has a wide range of applications. In the context of satellite imagery, It's a game changer for understanding the world of plants.
Hmm.
And right next to B08 is another helpful band, B8A.
B8A. So two NIR bands working together to give us a super detailed view of plant life. I'm seeing a pattern here.
Yeah.
It seems like each band provides a unique piece of the puzzle, adding another layer to our understanding of what's happening on Earth's surface.
Exactly. Think of these bands as different instruments in an orchestra.
I like that.
Each one plays a specific role,
Huh?
but when they all come together, they create a beautiful and complex symphony of data.
I love that analogy. What about the rest of the bands?
Well, the remaining bands shift our focus away from vegetation and towards other aspects of the Earth system. For example, B09 helps us track water vapor in the atmosphere, giving us insights into humidity levels.
So we can even track humidity levels with these satellites.
Yes,
That's wild.
it is. Then we have B10, which helps us identify those wispy, high-altitude clouds called cirrus clouds.
Cirrus clouds. Those are ones that look like brushstrokes across the sky, right?
Yes,
Beautiful, but probably not that helpful for seeing what's happening on the ground.
true. But knowing about cloud cover is crucial for understanding the overall quality of the satellite image. It's like factoring in the weather conditions before making any judgments about what you're seeing.
Makes sense. Now, what about the final two bands, B11 and B12?
Both B11 and B12 fall in the shortwave infrared region of the spectrum, or SWIRE for short. They're incredibly helpful for measuring the moisture content of both soil and vegetation.
Okay.
With these bands, we can tell if the ground is parched or soaked, which is invaluable information for farmers.
So we've covered all 13 bands, each capturing a different piece of the puzzle, giving us this incredibly detailed view of Earth.
Yeah.
It's amazing how much we can learn just by looking at our planet from above. But you mentioned something earlier about the Sentiwiki. What is that exactly?
The Sentiwiki, along with Sentinel Hub, is a fantastic online resource for all things Sentinel. It provides detailed information on each band's characteristics and applications.
Okay.
According to the wiki, the 5 major applications of the Sentinel-2 data are geophysical studies, land monitoring, maritime monitoring, emergency management, and security.
Wow, that's quite a range. From tracking crops to responding to disasters, these satellites are truly versatile. But how does all this raw data from the 13 bands translate into something that tells us, hey, that field is growing corn, or that forest is showing signs of stress?
That's where the real magic happens, and that's what we'll dive into next. The world of vegetation indices.
This is where things get really interesting. I can't wait.
So we've explored how the Sentinel-2 satellites capture light in 13 different bands.
Yeah.
Each revealing unique characteristics of the Earth's surface.
It's like having 13 different filters on a camera,
Yeah.
each highlighting a different aspect of the scene.
That's a great analogy.
Okay.
But the raw data from each band is just the starting point.
Right.
Scientists have developed ingenious methods to combine this data, creating what are called indices.
Indices, kind of like special formulas that unlock hidden information within the data.
Precisely. These indices reveal insights that wouldn't be apparent from looking at each band individually.
Okay, I'm definitely intrigued. What kind of hidden information are we talking about?
Let's stick with your interest in crop identification and focus on vegetation indices.
Okay.
These indices are specifically designed to tell us about the health, density, and even the type of vegetation on the ground.
So by combining the right bands, we can tell the difference between, say, a cornfield and a soybean field just from space.
Exactly. It all comes down to how different plants reflect light differently in those 13 bands.
Right.
Remember the red edge we talked about?
Yeah.
That plays a key role in many vegetation indices.
Right. The red edge, that sudden spike in reflectance in the near-infrared region, almost like plants are shouting, I'm healthy.
Exactly. Now, to answer your question about how we go from raw bands to meaningful insights,
Okay.
think of it like baking a cake.
Okay.
You need the right ingredients combined in the right proportions to get the desired outcome.
Okay.
Each index is like a recipe, using a specific formula to combine data from 2 or more bands, creating a single value that represents a particular characteristic of the vegetation.
Okay, so it's not just about looking at the individual bands. It's
Right.
about how they relate to each other.
You got it. And the Croatian researchers we mentioned earlier used 15 specific indices in their crop identification research, each one revealing unique insights about plant life.
15. That's a lot of indices.
It is.
Can we unpack a few key examples?
Absolutely.
Okay.
Let's start with the rock star of vegetation indices, the normalized difference vegetation index, or NDVI.
Okay.
It's a simple yet powerful index that's been used for decades to understand vegetation health.
NDVI, I've definitely heard that one before.
Yeah.
What makes it so special?
NDVI essentially compares how much red and near-infrared light a plant reflects.
Okay.
Remember, healthy plants absorb a lot of red light for photosynthesis
Right.
and reflect a lot of near-infrared light.
Right.
By calculating the difference between these two bands, NDVI gives us a clear picture of plant vigor, density, and even biomass.
So a lush, thriving forest would have a high NDVI value, while a struggling, drought-stricken field would have a low value.
Precisely. And the beauty of NDVI is that it can be used to monitor vast areas over time, allowing us to track changes in vegetation health due to things like drought, disease, or deforestation.
That's incredible. It's like having a pulse check for the planet's vegetation.
Yeah.
Now, what about some of the other indices those researchers used?
Another interesting one is the Green Normalized Difference Vegetation Index, or GNDVI.
GNDVI.
It's similar to NDVI,
Okay.
but instead of using the red band, it uses the green band, which, as we discussed, is strongly reflected by healthy plants.
So GNDVI focuses on the greenness of plants, giving us a more direct measure of chlorophyll content and photosynthetic activity.
You nailed it.
Yeah.
It's like comparing a plant's energy level, how actively it's photosynthesizing and producing food.
Right.
And because different plant species have varying levels of chlorophyll, GNDVI can even help us distinguish between certain crops.
Okay, so NDVI gives us a broad overview of vegetation health,
Uh-huh.
while GNDVI hones in on photosynthetic activity.
Yes.
What other insights can we glean from these indices?
Well, let's say you're a farmer concerned about drought conditions.
Okay.
The Moisture Stress Index, or MSI, would be your go-to tool.
MSI.
It uses the shortwave infrared bands to measure the water content in plant leaves, letting you know which areas need more irrigation.
That's amazing. It's like having a built-in moisture meter for your crops, all thanks to satellite imagery.
Exactly. And think about the potential for water conservation.
Right.
By using MSI to target irrigation only where it's needed, farmers can save precious water resources.
Okay, MSI for water stress.
Uh-huh.
What other cool indices are there?
Let's talk about the normalized burn ratio, or NBR.
NBR.
This one is used to assess the severity of forest fires.
Whoa, we can see burn severity from space.
You bet. NBR uses the near-infrared and shortwave infrared bands to distinguish between burned and unburned areas, allowing firefighters and forest managers to assess the damage, plan recovery efforts, and even predict future fire risks.
Each of these indices is like a superpower, giving us the ability to see things we couldn't see before.
It is. It really is.
And we've only scratched the surface.
Yeah.
There are indices for measuring chlorophyll content, detecting disease, estimating leaf area, and so much more.
There are so many.
This is truly mind-blowing. By combining the right bands, we can create indices that unlock all sorts of secrets about plant life.
Precisely. And here's something else to consider.
Right.
Remember those 15 indices used by the Croatian researchers?
Yeah.
Well, their research revealed that some Sentinel-2 bands, like B06, B8A, and B10, weren't even used in those indices.
Wait, really? So there's potentially even more information hidden within the Sentinel-2 data that we haven't even begun to tap into.
Exactly. And that's what's so exciting about this field.
Right.
There's still so much to discover and explore.
Yeah.
Who knows what other insights we could gain by combining different bands or creating new indices.
This has been an incredible journey so far.
It has.
From capturing light in 13 different bands to creating indices that reveal the hidden lives of plants, it's amazing how much we can learn just by looking at our planet from above. But before we wrap up, I have to ask, what are some of the limitations of using satellite imagery and indices to understand plant life?
That's a great question.
Yeah.
While this technology is incredibly powerful, it's not without its limitations.
Okay.
Factors like cloud cover, atmospheric conditions, and even the time of day an image is taken can affect data quality and interpretation. And while indices can provide valuable insights, they're not always perfect substitutes for on-the-ground observation.
Well, that makes sense.
Yeah,
Like any tool, it's important to understand its strengths and limitations to use it effectively.
absolutely.
So we've explored the how of capturing and analyzing data from the Sentinel-2 satellites.
Right.
Now, let's dive into the why, the real-world applications and implications of this technology in our final segment. So we've gone from, like, dissecting the electromagnetic spectrum to unraveling the mysteries of plant life with these incredible indices.
Yeah, it's really fascinating.
And what's even more exciting is how it's being applied to solve real-world problems. For instance, imagine being able to track the spread of crop diseases in real time.
Exactly. With satellite imagery and indices, we can identify areas where crops are showing signs of stress or disease before the damage becomes widespread.
Yeah.
This allows for early intervention, potentially saving entire harvests and preventing food shortages.
That's like a game changer for agriculture. And it's not just about crops. We can use this technology to monitor forests, identify areas affected by illegal logging, and track deforestation patterns.
Absolutely. It's
Yeah.
like having a watchful guardian over our planet's vital ecosystems. It provides crucial data to inform conservation efforts and protect biodiversity.
This is all incredibly impressive, but I'm curious, are there any limitations to using satellite imagery for these applications?
Well, one challenge is the resolution of the images.
Hmm.
While satellites like Sentinel-2 provide incredibly detailed data, they might not be able to distinguish individual trees or small patches of land.
So for really fine-scale analysis, you might still need to rely on drones or on-the-ground observations.
Exactly. But even with that limitation, satellite imagery provides a powerful tool for large-scale monitoring and assessment.
Right.
And with advancements in technology, the resolution of satellite images is constantly improving.
That's good to know. So we've talked about the applications in agriculture and environmental monitoring, but I'm sure there are countless other ways this technology can be used.
You're absolutely right. Think about disaster response.
Okay.
After a hurricane or wildfire, satellite imagery can be used to assess damage, identify areas in need of immediate assistance, and guide relief efforts.
Or even urban planning. By analyzing vegetation cover in cities, we can identify areas that would benefit from more green spaces or assess the impact of urbanization on the environment.
Precisely. The possibilities are truly vast and constantly evolving. What strikes you as the most compelling aspect of this technology?
Honestly, it's the sheer potential for positive impact. From improving food security to protecting our planet's natural resources, satellite imagery and indices are giving us the tools to make more informed decisions about our world.
I couldn't agree more. It's a testament to human ingenuity and our ability to harness technology for the greater good.
This has been an incredible deep dive. We've gone from understanding the physics of light to exploring the intricate world of plants, all through the lens of satellite imagery. It's amazing to think that we can gain so much knowledge about our planet simply by observing how it interacts with sunlight.
And the most exciting part is that this is just the beginning. With continued advancements in satellite technology, data analysis, and machine learning, who knows what incredible discoveries await us.
Well, there you have it. From capturing light in different bands to deciphering the secrets of plant life with indices, we've explored the incredible power of satellite imagery and its potential to shape our understanding of the world. But as we wrap up, I'm left with a thought-provoking question for you, dear listener. What if we could combine this technology with other data sources like weather patterns, soil composition, and even economic trends? What new insights might we uncover, and what innovative solutions could we develop? The possibilities are truly endless. Keep exploring, keep questioning, and who knows what groundbreaking discoveries you might make.